Okay. One more thing, I guess, kind of an announcement before we get started. There won't be a map of this week. I tend to try to announce those things because it's first Friday and we all get stuck in here. So enjoy your first Friday and get back to this week after. Please try to be mindful when you do quizzes, when you upload them, try to make sure that your file is clear and readable up there. Okay, questions? All right. So what we're going to talk about today are functions, sort of. Functions were a simple part of what you all did in calculus, right? I mean, what did you do? You had a bunch of functions, you drew pictures of them, you took derivatives, then you integrated them. Functions were a simple part of calculus, they're a simple part of mathematics. I think it's 1 point something anyway. Yeah, it's linear transform. So first, I want to go back in time a little bit. So what is a function, right? What did you all do in calculus? It was always this business of y equals f of x, right? Can somebody describe to me what a function is? Yes.
It takes an input and it maps it to a result.
I'm sorry.
It takes an input and it maps it into a result.
Okay, that's a good kind of intuitive way to think about it. It's like a little black box, and you put in well, in calculus, let's just restrict it there. What you did in calculus, you take a real number and you put it in there, and it barks out some other real number, right? And you can draw a picture of this or something like that. And there was also kind of a caveat, as I remember, with functions that given any input, there is a unique output. Does anybody remember what that was for? Why do we say a unique output? Yeah.
Because if you had two outputs for the same input, then it would be like an undefined function.
That's right. It's not really a function. So when you put something into your black box, you want to always be able to predict what comes out of it, right? Let me give you an example of something that's bad. If I give you complete freedom on square roots and I say, okay, what's the square root of 25? What would you answer? You'd answer 5. But what else might be a legitimate answer to that? I think it's 2. Well, -2. Well, how about -5, right? Everybody agree with that? And that's why, if you remember back in the calculus days, when they defined the square root function, they said we always take the positive square root of the number, right? This forces it to be a function. That's what I mean by unique output. When you put it into your black box, you don't want there to be any ambiguity about what's coming out. You want to be able to predict it. Well, a function in calculus is something that you took a number and it gave you a number, right? In linear algebra, what's a function going to be? I bet you input a vector and you get out a unique vector, right? So for linear algebra, we have a function, and I'm going to call it oftentimes T, linear transformation, from Rn to Rm. And B, if D is a vector in Rn, T of B is a unique vector in Rn. Your input, a vector in Rn, your output, a vector in Rm. Let me give you some sort of terminology to go for this. the domain of T is, does anybody remember, this is no different than, you know, functions and pre-calculus. What's the domain? I'm sorry? Right, the X value which lives in Rn, right? So the domain of this is Rn. The domain is just all the garbage that you can put into your black box. It's just all the stuff that you can plug into the function, so it's everything in R. Rm is the, some of you may want to say range. I'm going to call it the code, or sometimes the target. It's just where you go, right? How many of you were expecting me to say range? Right, yeah. Range is something slightly different. I'm going to give you an example of this. This is just everywhere that the vector can go, right? This is actually a subset of, I didn't write it. This is actually a subset of R view. Let me give you an example of the difference here. Let me give you an example. I'm going to define a function via a matrix. Right, and I'm going to tell you what I'm going to do. I want to try to build a function. And I'm going to see if I can make kind of a cool rule here. I'm going to define T of X to be AX, where A is following matrix. I'm going to do 1 minus 1, 0, 2, 3, 5. And I have designed this particular example to show you why I'm mucking around with this language here between codomain and range. So I'm going to define this function T of X to be your input is a vector, a 3 vector, and its output is this matrix times a 3 by, or a 3 by 1 matrix, or a 3 by 1 vector. What happens when I take this 3 by 3 matrix and multiply by a 3 by 1 vector? What am I going to get? A 3 by 1 vector. So here we go. Input a 3 vector, output a 3 vector. Okay, so far. So here my domain is R3, and my codomain, my target, is also R3. Right? But we'll see actually this example range is a little bit different. So let's get down to brass tacks and see how this works. Let's take the vector and see what happens to it. It should be so let me compute this. This is 3 by 1 vector, and let's see what we get, shall we? The top row should be this row times this column, so it should be x1 minus x2. The middle entry in this new vector should be second row times this column. about my bottom entry in this vector? What should it be? It should be zero, right? Because no matter what values I add here, I'm gonna get zero, right? Everybody agree with me? The codomain is R3. Is the range of this R3? Is every stinking vector in R3 in the image of this? Can somebody give me a vector in R3 that's not possibly in the image?
Is it 1, 1, 3 because you have the 0 vector for Z?
What's that? What do you mean, 1, 1?
Well, I mean, you have a 0 vector for the common.
That's not the zero vector, that's just zero entry. Can anybody give me a vector that no matter what values for x1, x2, x3 I put in here, there's no way I'm getting that 3 vector out of it? Is it possible for me to choose values of x1, x2, and x3 and suddenly get, I don't know, 0, 0, 1? That is not possible. Everybody agree? You cannot get anything except for vectors that have a 0 in the last entry, right? You can't get 1, 2, 5. Impossible. You can't get anything that has a 0 or anything other than 0 as the last entry, right? The range of this is not all of R3 because there's a whole bunch of it missing. Everybody agree with that? That right there is the difference between the codomain and the range. The codomain is just where I said it's going, right? Output a 3-dimensional vector. And that's what I got, a 3-dimensional vector. The range is actually everything that's covered. And I'm not completely sure of the range. I think I've probably got complete freedom in the first 2 coordinates, not sure yet. But I know for a fact that I can't cover everything because the last coordinate always has to be 0. Is everybody okay with it? Okay. Let me point out that you don't have to have one of these things going from R3 to R3. Let me give you a quick example here, another concrete example. So let A be the vector 3, 0, 1, 5. And I'm going to use this I'm going to do just like I did in the previous example. I'm going to use this matrix, this multiplication by a matrix, to define how this function works. My input is a vector. I'm going to multiply this by a vector to get an output, right? But riddle me this. I'm doing this in a slightly different order than I did last time. Where am I going here? Right? Last time this matrix went from R3 to R3. Now all I've given you is the matrix. Where does my input need to be? My input's vector. Where does it need to be? Anybody? Bueller? Okay, so riddle me this. What's the size of this matrix?
2 by 3.
It's 2 by 4 for sure, right? So to make this multiplication work, your input has to be what size vector? Very good. So this better go from R4. Your input needs to be a 4-dimensional vector. And what are you going to get cubed out of this? R2. Has to, right? And let's watch this in action. So. And of course, you should be able to sort of directly see this work. X1, X2, X3, X4. This should be this matrix here, which is 3, 0, 1, 5. Minus 1, 1, 2, 4. And I'm going to use this matrix to act on this crazy four-dimensional vector. Good Lord willing, the creeks don't rise. This is going to give me a 2x1 vector. Let's see what happens. This row times the column, so that's going to be 3x1, 0x2, 1x3, 5x4. And next entry is this times the column. I get minus x1 plus x2 plus 2x3 plus 4x4. And notice that this gives, for example, a formula for how this function works. For example, t of, I don't know, 1, 1, 1, 1, make it easier on you. Well, now you've got x1, x2, x3, x4 all equal 1. See what your formula tells you. That should be 9. And that should be 6. For example. And notice that every input, no matter what vector I pick, will give me a unique output. Any questions? Okay. Let me do one more thing here. Let's go back to this previous example. We have T R3 given by T x1, x2, x3 is equal to 1, 0, 2, 3, 5, 0. Okay, so let's go back to this linear transformation we were looking at before. By the way, so far, the only thing that I should have convinced you of is these are in fact functions, right? Your input is vector, you multiply by some fixed matrix, in this case, that 3x3 matrix, and you get an output to vector, right? What do I mean when I say linear transformation? Well, it may be kind of a hint that this is sort of not just any old function, but it's got some other properties, and we'll discuss what that means. So this is the vector x1 minus x2. This is 2x1 plus 3x2 plus 5x3. Find all vectors x and on 3 such that E of x is equal to 0. Let's find all vectors such that when you plug that vector into this function, that is, you multiply by this matrix, you get 0. Now, I'm not just running the stall here, this is actually rather important. The set of vectors for any linear transformations, it's C of x 0 is actually a very important thing called the kernel of the transformation that we will study later. So this will actually have some applications to see later, but for now, let's just kind of see if we can figure out what are the vectors that map to zero vectors. By the way, without even looking with my eyes closed, I know one of them. Anybody give me one solution? The zero vector, like that one's always got to work, right? Maybe it's only the zero vector, but let's see. So this is the reason I was doing the example is because it's kind of takes it. Like today, what we're doing is this is the same as finding solutions to homogeneous equation. So let's do that. Really what we're doing is we're solving this system of equations, which I'll put in the augmented form, even though it's homogeneous. We're trying to find all vectors such that this, when you multiply it, it's 0 for 0. Okay, so now I have put this, I put this in the augmented equation. Now, the original problem is finding all vectors in R3 such that T of x equals 0. That's the same thing as solving this equation for zero vector, and hence that. Now, you all already told me the zero vector is a solution. Good for us, we know that. And I seem to remember that in linear algebra, if you've got at least, so we've got one solution, right? So it's consistent. The question is now, do we have one or infinitely many? Now, I haven't solved this yet, but can you all put your eyes on this and tell me what's the answer? Are we going to have just the zero vector, or is there going to be more solutions? Okay, what's the dead giveaway here? Yeah, the freaking row of zeros on the bottom, right? I mean, we've got at least one free variable. So let's go ahead and actually do what's asked of us to find the solution. I'll use this to eliminate. And I just love homogeneous because I don't care what manipulations I do here, I'm always going to put zeros in that last column. Multiply this by -2 and add. -2 and add. And so this is 1 minus 1, 0, 0, 1, 1. And just to make my life easier, I guess I can do one more step to get the row of this section on the form. Row of zeros on the bottom. And 1, 0, 1. Right, okay. So these equations, I get x1, 3, 0, and x2 plus x3, 0. Okay, so looks to me like I got two basic variables, right? X1 and x2. X3 is free, doing its free thing. And so my solution looks like this. X3 just is what it is, but it's free. And this equation tells me that x2 is negative x3. And this equation tells me x1 is negative x3. And so notice x3 is a constant, so I can pull it out. So what are the vectors that I can plug in and plug into this function and get the zero vector? It's any vector that is x3 times s. So in other words, two entries here are the same and the third negative, right? Again, I can't emphasize this enough, and not just in this class, but probably any class that you all have, physics, whatever. A lot of these things are checkable, right? For example, just let x1 and x2 be the same thing and x3 be the opposite sign of them. If x1 and x2 are the same thing, you get a zero here. And if these two are the same and this is the opposite sign, you get a zero here. So notice when I plug in any vector of that form, I get 0, 0. Okay. Any questions? So I'm gonna do some more examples too, but I can't resist anymore. I think I'm gonna tell you all what linear transformation is. Um, we say the function P with domain Rn and codomain Rm is a linear transformation if two things. There are two things to make it linear. Number one, if you have u plus v, if you add up two vectors inside there, this is the same thing as t of u plus t of all u v in the domain. So you can break apart sums this way. T of u plus v is always t of u plus t of v. And number two, t of c vector. This is a constant. I'll make it clear in a moment. What this basically says, I can pull out constants. So you can scale outside the transformation. For all vectors in the domain and C a number. This is what a linear transformation is. Now, this is actually a generalization of basically multiplying by a constant in reals, right? Here's some very familiar functions that you have in calculus. Y equals 2x, y equals 3x, y equals negative x. In fact, y equals mx. Any line through the origin is a linear transformation. It's fairly easy to check. And this is a generalization. When you have larger dimensional space like R2 or R3 or whatever, you've got a lot more freedom with what these things can do. Let me give you a large class of linear transformations. Let A be an n by n function. Okay, any matrix you want, then the function, and this this is what we've just been doing all day with our examples. The function from Rn to Rm given by multiplication by this matrix. So your input is an n by 1 vector. So this is an n by n matrix and an n by 1 vector, and its product is an n by 1 vector, right? X is n by 1, A is n by n, so the AX is n by 1. This function is what we've been doing in every one of my examples of this, but here's something that I didn't show you. That's cool. So what this theorem says is every one of these functions that I've had that's multiplication by a matrix, every single one of them was actually one of these linear transformations. And let me prove it because it's easy, but I think it's important to see these things are really what I claim they are. To show that something's a linear transformation, the burden is upon me to show that these two things work. But I feel like you're gonna go home and take a shower. I feel a little dirty because it's gonna be really easy because we already know the properties that we need to make this work. So let's go through. Let's start here. T of u plus b. What is my rule? My rule is T of, what do I do to the input? I multiply it by the matrix A. That's how the function works, right? And what do I know about multiplying a matrix by a sum of two vectors? What's another step that I can take here? Okay. That's one of the properties that we had before, right? And what is AU? See, I feel so cheap or something. AU is TU and AV is TV. And there you go, it works. Right? So there you go. There's the first one. Part two, right? We've got to show that this second thing works. That is, you can pull out the scale out of the function. We'll see how that goes. Again, my rule is T of CV is just multiplying the matrix by CV. And what can I do here? Right, you can pull out the C. That's another one of my matrix rules that we had before. And this is C. There we go. It works again. So multiplication by matrices is a large class of examples of linear transformations. Everybody cool with that? I've got some great news for you. These are the only linear transformations. That might not be so obvious, but it turns out that if I walked up to you on the street and give you a linear transformation from Rn to Rm, you can write that sucker as matrix. And we're going to learn how to do that. Let me tell you why it might not be so obvious. Well, before I tell you why it might not be so obvious, let me give you a couple of observations. Here's another theorem. Yeah, T from Rn to Rm is a linear transformation. Then here are two things to follow, but they're noteworthy, and it will be useful later. T of the zero vector equals the zero vector. And actually, be careful, I'm gonna write it that way. Because let me point out, these might be zero vectors. This vector here is a vector with n rows, so it's got n zeros in it. This vector is a vector with n rows, right? So they're the zero vector, but they could be silent. And two, T of AU plus BB is ATU plus BT. A, B numbers, and U and B vectors in R. So in other words, instead of doing it two steps, you can just break it up this way. Let me demonstrate why this is true. Prove these. First of all, T of the zero vector well, let me point out that everybody agree with that bit of foolishness? The zero vector is 0 times the zero vector, right? I mean, what does old Jimmy do? But check out this property. That 0, I can slide out in front. And any vector, I don't care what this is, comes a zero vector, it's 0. So there you go. This is always true for linear transformation. If you plug in the zero vector, you have to get the zero vector, always. And the second bit, I'll let this theorem up on the board here, right? Because this says that T of vector 1 plus vector 2 can be broken up this way. So this is T of vector 1 plus T of vector 2. Right? And then I will 2 times use the second property that says I can pull those numbers out in front. Everybody okay with that? So this is kind of a shorthand. It's good to know. Okay. Let me give you some examples of linear transformations. So I'm going to give you kind of a simple one first. Here's a simple linear transformation. Actually, let me pull up on that. I'm going to do that in a minute. Let me start with something simple. T of V equals B. Right? This is just the identity, right? It takes any vector and what vectors to give you back the same vector. It's easy to check that this is linear transformation, right? Because T of U plus B is U plus B, right? And T of AB is AB, so it works. So what if this is? Can anybody think of a way? I mean, I've told you that it turns out that every linear transformation from Rn to Rn is a matrix. But I haven't really justified that yet. Can anybody think of a way to write this as a matrix? Anybody think of a matrix that I need? Multiply the vector xy and get the vector xy back. What happens? 1, 0, that gives me an X. 0, 1, that gives me a Y. Everybody okay? Anybody want to nuance this? What if I go from Rn to Rn to Rn? So what matrix times x1, x2, xn can spit out the same vector? Well, yeah, it will be, but can you completely describe the entries of the matrix? Yeah. Okay. So it should be the matrix that consists of ones down the diagonal. It has to be a square matrix because same size. Ones down the diagonal and zeros everywhere else. Everybody agree with that? This is called I sub n is n by n identity. Very important. Even though it describes very easy linear transformation, it's a very important matrix. Let me ask this, it's up voltage a little bit. What if I asked you to do this? Let me convince you that this is a linear transformation. One, notice T of Q plus B is 2. B plus 2U plus 2B, which is T of U plus T. So there, it satisfies the first part of linear transformation. Also, T of CB is 2CB, which is C times 2B, which is CT of B. So multiplication by 2 is a linear transformation. In fact, multiplication by any number is a linear transformation. Can somebody want to guess how you would describe this matrix? Yeah.
Matrix times 2.
Right, and that's essentially it. It's the identity. Multiply this matrix by 2, so it should be where A is 2, 0, 0, 2, 2. And actually, you can generalize this to any number. For example, multiplication by 0 should be the matrix with all zeros in it, right? Which would be 0. Okay. Any questions on that so far? okay, I've given you all a couple simple transformations. And maybe we've sort of semi-convinced ourselves that, okay, these things can be written in matrix. But there are certainly things that are more exotic, right? Here's an example. Let me just give you a matrix. Let's do this. Well, so I'm going to give you this linear information. This one might be a little bit of a trick. So I'm going to describe this instead of multiplying by matrix. Rotate the 90 degrees counterclockwise. So T actually goes to mark your clock. So let me sort of point out what this thing does. This linear transformation will take any vector, say this one right here, and it will take the same size. It rotates 90 degrees counterclockwise and goes to this. It will take this vector and it'll go to this. Right? So the best way I can describe this is imagine that God put his hand on the plane and rotated it 90 degrees counterclockwise. That's the way this linear transformation works. It takes every vector in the plane. It basically just screws the plane 90 degrees counterclockwise. Everybody okay with me? Now, let me point out that this is a linear transformation. I'm going to be a little sloppy at this, but if this is U and this is V, then U plus V by the parallelogram law is that. Everybody agree? And notice when I rotate this whole parallelogram 90 degrees counterclockwise, I still get what it's supposed to be, right? Notice that since the vectors don't change sides, the scaling works as well. Everybody agree with that? This is a linear transformation, right? Notice that the zero vector stays there because the zero vector has no size. It just stays right there as you spin it, right? Everybody okay? This is a transformation. What's the matrix? I know the matrix. This one's actually not too bad to get. I'll let you puzzle on that for a while. This one's actually not too bad to get. But what if I change this display? What if instead of 90 degrees, I wanted to go pi over 3, right? Suppose I wanted to go pi over 3 radians counterclockwise. That should be a linear transformation too, because it's the same rotation, it's just you didn't go quite as far, right? What would the matrix for that be? I mean, I did make this wild claim that every linear transformation can be written as matrix, right? And with the first few examples, it seems obvious, but maybe this one is not so obvious, right? I mean, can I write this as matrix? And the answer is yes. And I'm not going to spoil the surprise, but for next time, why don't you kind of see if you can think about that? I'm going to show you next time in class, actually, how to get your hands dirty and figure out what that matrix is. This is a matrix. Here's another one. You guys remember taking derivatives, of course. if you go from the collection of polynomials, what happens, does anybody remember what a polynomial is?
But you can give the definition, it's a, it's a function with a higher degree, what is it, it's either 3 or 4.
What you mean?
Yeah,
A polynomial is something that looks like a number plus a number times x plus a number times x squared plus a number times x cubed, and you stop at some, right? For example, x to the 5th plus x squared plus 27, right? Everybody okay with that? What happens when you take the derivative of a polynomial? What do you get? Do you get sine x? No, you get another polynomial.
That's like an order lower.
Yeah, it'll have a lower degree. That is correct. You might check that taking the derivative of polynomials is a linear transformation. It will have a matrix too. Right? You can actually do differentiation stuff you didn't calculate as a matrix. So you can figure out how to do that. And if there aren't any questions, we'll reconvene next time.